I present you our study on boosted decision tree regression adjustment for variance reduction in online controlled experiments that we did in Yandex with my colleagues. I will start with reminding the key points of A/B testing. So there are some users of a web service. First, we split them randomly in two groups. Second, we expose them to one of two variants of the service, for example, the current production version or its update. Then we calculate a key metric for each experimental unit. For instance, we calculate the number of sessions for each user. And finally, we calculate the overall evaluation criterion for each group as the mean value obtaining, for instance, sessions per user metric. Having the OEC value for each group, we calculate the difference between them and compare it with 0. So we calculate this difference and compare with 0. Thus, we decide whether the evaluated update is positive or negative for our service. Finally, a statistical significance test is applied to determine whether difference is caused by noise or the treatment effect. Usually, the state-of-the-art student's test is applied. The combination of an OEC and a statistical test is referred to as an overall acceptance criterion. The ability of the metric to detect the statistical significant difference when the treatment effect exists is referred to as the sensitivity. The higher the sensitivity, the smaller changes one of the service could be detected by an A/B experiment, or alternatively, the smaller user traffic could be used to detect changes with the same magnitude. Now we are ready to consider our approach of sensitivity improvement. Actually, the difference delta x is an unbiased estimator of the average treatment effect, which is defined by this equation. Let us assume that we have a feature vector of a user, and then we decompose the metric in the following three components. The first term is the expectation of the key metric with over users with the attributes f, this one. If you can, okay, I will show in this slide. The second term is the expectation bias of the metric for users with a given assignment v. It is this term. And the last term is a noise. By definition, for each term, one can calculate its ATE and its variance that give us the following identities. We see that the first term has no impact on the ATE, but may increase the variance. We see that it is 0 here, but we can remove it. Therefore, we can try to estimate this component and subtract it from the metric. So let P be a predictor of x based on the features f. In our work, we propose to use the following modification of the source metric x. For each user, it is the difference between the actual value of this metric x and its predicted value. In order to analyze our new metric, let us consider the following assumptions of the predictor. First, the predictor does not depend on treatment exposure. The predictor minimizes the root mean square error in a class of learning models, which is closed under addition of a constant and closed under scalar multiplication. Note that these assumptions hold for linear regression model and Friedman's gradient boosted decision trees. So the independence on treatment exposure implies that the average treatment effect of the modified metric y is equal to the 1 of the source metric x. Thus, delta y is a biased estimator of average treatment effect of the source metric x. And the metric y is thus consistent with this source metric x. The optimality in a class closed under addition of a constant implies that the variance of the modified metric is equal to the mean square error of the predictor. Hence, the better the predictor, the lower the variance of the modified metric y is. And thus, the better sensitivity of this new metric is. On the other hand, the optimality in a class closed under scalar multiplications implies that the variance of the modified metric y is lower than the one of the source metric x. Hence, we have variance reduction with respect to the source key metric x. And the novel metric improves thus sensitivity. I remind that student's t-test is based on the t-statistic. And we can see that having some variance reduction rate lambda, a proportional reduction of the number of users participated in A/B test results in the same variance of the delta. Due to we have this equation. So it is equivalent to the same value of t-statistic when we reduce the variance, but also reduce this number of users. So thus we have that variance reduction rate is equivalent to saved user traffic rate. And the modified metric y saves thus user traffic with the same sensitivity level. So we have the following summary of our theoretical guarantees on our novel metric. First, the metric y is consistent with the source metric x, and thus we can make the same decisions given the treatment effect collected from changes of the metric y. The metric y improves sensitivity, and the better the prediction quality, the better sensitivity of the metric y is. And finally, the metric y saves user traffic if we want to have the same sensitivity level. If we do not want to increase sensitivity, we can have the same sensitivity level, but we can use less users, and thus we can conduct more A/B experiment in one day. The final section concerns the experimental validation of our approach. We considered 161 A/B experiments conducted on real users of Yandex. One can see that the number of users in these A/B tests varies from 500 of thousands to 3 millions here. And the duration of experiments varies from 1 week to 1 month. In our prediction, we used the following 51 features. The first one features is our main feature. It is the metric value over 14 days before the A/B experiment. It actually is, if we consider the number of sessions of a user and we have an A/B experiment, we take 14 days before this experiment and calculate the number of sessions for each user during this previous period. Next, we considered time series of daily values of this metric during this previous 14 days period, and also cumulative values. So overall, we have 27 features. Third, we considered features like cookie timestamps, for instance, creation time of the user's cookie and the user's first entrance to the A/B test. Overall, we considered 3 features. And finally, we also transformed the daily time series in different ways, obtaining features like Fourier amplitudes, entropies, and etc. We considered overall 20 features. In our work, we studied two prediction models classes. It is linear models and ensembles of decision trees that are the state-of-the-art advanced machine learning approach. In our study, we consider the following baselines. First, it is the state-of-the-art number of sessions as our non-modified source key metric X. Second, we consider this metric X adjusted by linear model constructed over the only one feature, which is the total feature or the number of sessions before the experiment. This technique is also known as Cupid in online A/B testing. And finally, we considered this metric X adjusted by linear model constructed over the all features known as linear regression adjustment, which is widely applied in clinical trials, and it is well known in literature on variance reduction techniques. We evaluate the performance of our approach in 3 criteria. First, we evaluate the prediction quality in terms of normalized root mean square error. Second, we evaluate variance reduction rate. And finally, we evaluate sensitivity improvement in terms of success sensitivity rate, which is the number of A/B tests with detected treatment effect by this metric X divided by the whole number of A/B tests. So in this table, we present comparison of feature sets and models in terms of different performance evaluation criteria over all studied A/B experiments. We see that our approach outperforms all baselines, demonstrating 63% of improvement with respect to the variance reduction rate. So in this column, we have experiments on variance reduction rate. And if we assume that the variance of the source metric is 1, our best metric Y demonstrates approximately 63% of improvement. So we reduce the variance approximately in 3 times, which is equal to 63% of saved traffic, as I said before. Also, we see that the number of A/B tests with the detected treatment effect increases twice. It is the right column. It's here. Finally, we demonstrate the performance of the approach with respect to the duration and user traffic of an A/B experiment in terms of both normalized root mean square error and variance reduction rate. We see that on the one hand, both prediction quality and variance reduction has very low dependence on the number of users participated in a B experiment. It is, this charts. So we have that approximately are the same for users. On the other hand, prediction quality depends noticeably on the duration of an experiment. One can see on these charts. But variance reduction rate depends only slightly on this duration of A/B experiment. We explain it by the following knowledge that actually z-score increase, and thus if you just consider the proportion between the normalized root mean square error variance reduction and z-score, you will see that actually it is normal situation for us. So overall, we get the following results for the state-of-the-art sessions per user metric. 63% of variance reduction achieved, 3 times less user traffic needed, and 2 times more A/B tests with detected treatment effect. And you could take away the following key points. So we should subtract the predicted value from the key performance metric to get this or such results. We should apply advanced machine learning techniques like gradient-boosted decision trees to predict the key metric, not only linear models like before. And you must use features that are independent of the treatment assignment, which is the key point of this study. So, thank you. Questions?
Thank you very much. Are there any questions?
Hello, could you give more explanation about the metrics you're using in the evaluation? For example, the variance reduction rate, what's that?
Variance reduction rate, it's just, we consider our novel metric y, and we consider the source metric x. For instance, the number of sessions. So x is the number of sessions for a user, and y is the difference between the actual value, actual number of sessions, and the predicted number of sessions. And then we calculate the variance between y and we calculate variance for this metric y over all users and calculate the variance for metric x over all users in our A/B experiment.
But why does the variance reduction more means better?
No, it means that if the rate lambda is less, then it is better. I can give you. So you could see that the higher the t-statistic, the higher the sensitivity rate. Thus, we should decrease the variance. The variance, it is this component.
Okay.
So if we decrease the variance, we increase the statistic, and thus we increase the sensitivity.
Yeah. Okay, so I think we can take that part offline, but there's maybe time for one more question before we. Maybe the next speaker can already start setting up.
Thanks for the great talk. This approach seems to be very sensitive to the prediction, the actual prediction. And
right.
Can you comment on if there is a bad prediction model, what would happen to the success rates? And also how the success rates in terms of sensitivity metrics is calculated. Do you have something that is shown offline an improvement, and then you calculate the rate of A/B test that shows that also in the A/B test? How is that sensitivity metric calculated?
So I'll try to answer to the last question.
So my first question was how would this approach perform if the prediction is bad? It seems to be very much dependent on how good we do with the prediction.
Actually, we have some theoretical guarantees, for instance. For instance, if your predictor have a bad root mean square error, thus you have a bad variance, so you have the larger the error, the larger the variance, and thus we can have or moderate reduction rate, or even we can have a larger variance than of the metric x. So, and the second is about how we evaluate it, right?
The success and the sensitivity.
So we evaluate sensitivity in terms of just in terms of success sensitivity rate. We just take a set of A/B experiment in our study, we considered 161 experiments. And we just calculate t-statistic for our metric, derive the p-value, and using our threshold that we used 5%, we count the number of A/B tests where we detected the legitimate effect, where the p-value is less than 5%, and thus we calculated the sensitivity rate. So we did it for our production A/B experiments, and this technique is applied in our production.
Okay, let's thank the speaker again, and thanks for so patiently answering questions.